Welcome to the Explainer. Okay, let's dive right into this. If you're currently studying for your CCNA, Network Plus, or maybe a brutal university networking final, you already know the pain. These exams can be absolutely relentless. They are just packed with abstract layers, obscure protocols, and really tricky, convoluted scenarios. But don't stress, because we've designed this explainer to be your ultimate cheat sheet. Today, we're completely cracking the TCP IP code. We're going to tackle the exact types of high-stakes questions your professors love to throw at you, and we're going to make these concepts so simple and clear that they'll be basically impossible to forget.
So here's our game plan for today. First, TCP IP and OSI basics. Then, Layer 1, network access. After that, Layer 2, internet, followed by Layer 3, transport, and Layer 4, application. Finally, we'll tie it all together with a real-world scenario. Let's get right to it.
Section 1. TCP IP and OSI basics, the blueprint of the Internet.
Think of the TCP IP model as the fundamental standard that makes the entire modern Internet possible. It's honestly a lot like a highly efficient global postal service. You have an address you want to send a package to, right? And you need a guaranteed system to make sure it gets there intact. Now, how does this compare to the older, theoretical 7-layer OSI model? Well, TCP IP elegantly condenses those 7 OSI layers down into a much more streamlined 4-layer stack. The top 3 layers of OSI, that's application, presentation, and session, are all mashed together into just the application layer. And down at the bottom, the OSI data link and physical layers are merged into the network access layer. You definitely want to memorize this mapping because professors absolutely love asking you to translate between the two on exams.
Moving on to Section 2, Layer 1, network access. Getting physical.
At this foundational layer, we are transitioning away from abstract data and getting down into the actual physical wires. We're talking copper cables, fiber optics, and Wi-Fi radio waves. Now, here's a classic, high-stakes professor question that trips up a ton of students. If we already have logical IP addresses, why do we still need physical MAC addresses? Well, the crucial difference is that an IP address tells you where a device is located logically on the internet, kind of like a zip code. But the 48-bit MAC address, that's the permanent physical identity stamped literally right onto the device's hardware at the factory. You absolutely have to have MAC addresses for local hardware-to-hardware communication before your data ever even touches the wider internet.
Let's look closely at how data actually travels down here at Layer 1. We call the data unit at this level a frame. Think of a frame as the packaging. It wraps up the payload data and slaps on a source MAC address and a destination MAC address. Oh, and this right here is a guaranteed test topic, the CRC, or Cyclic Redundancy Check. This little piece of data sits at the very end of the frame, and its entire job is to check for physical transmission errors. If your frame gets corrupted by interference while traveling over the wire, the CRC catches it instantly.
Before we climb out of Layer 1, we really need to talk hardware. You are almost certainly going to see a question asking you to contrast a hub and a switch. The simplest way to remember it: a hub is fundamentally unintelligent. If a hub receives a frame, it just blindly shouts it out, broadcasting it to every single device plugged into it. A switch, however, is smart. Switches operate by building MAC address tables to learn exactly which computer is sitting on which port, and then they quietly route the data only to the intended recipient. Switches completely rule the local network.
All right, Section 3, Layer 2, Internet Protocol, navigating the globe. We're stepping up the stack now, leaving your local Wi-Fi network behind and entering the wild world of complex global routing. Consider this classic exam scenario. How does a device in New York actually find the exact path to a specific server in Tokyo? The answer lies in IP addresses and routers. Unlike those local switches we just talked about that only care about MAC addresses, routers operate right here at Layer 2. They look at your 32-bit IPv4 address, something like 192.168.1.1, or the massively upgraded 128-bit IPv6 address, and they use it to calculate the absolute best path across the globe to reach that exact destination. To really ace this, we need to fully grasp a core networking concept: encapsulation. Just think of Russian nesting dolls. As data moves down the network stack, every single layer wraps it in a brand new layer of information. At Layer 2, the data is encapsulated into a packet, which holds the source and destination IP addresses. But wait a second, how do we link this logical IP address back to a physical MAC address when it finally arrives? Enter the ARP protocol, the Address Resolution Protocol. ARP brilliantly translates IPs into MACs,
perfectly bridging the gap between Layer 2 and Layer 1.
Let's keep moving up. Section 4, Layer 3, Transport Layer, the delivery service.
Okay, getting the data to the right computer using an IP address is fantastic, but your computer runs dozens of programs at the same time. How does the network know to send the incoming data to your email app and not your web browser? That brings us to port numbers and protocols. And here is the ultimate exam trap question. If TCP guarantees delivery and is way safer, why would anyone ever choose to use UDP? It seems completely counterintuitive, right? Why pick an unsafe protocol? Let's break down this legendary networking battle.
So TCP is what we call connection-oriented. It's the perfectionist. It numbers every single segment of data and guarantees delivery in the exact right order. If a piece goes missing, TCP literally stops everything and asks for it again. This is absolutely vital for web browsing and emails, where a missing chunk of data ruins the whole file. UDP, on the other hand, is connectionless, the speed demon. It just throws the data at the destination as fast as humanly possible, without even checking if it arrived. Why use it? Because raw speed beats perfection in scenarios like live video streaming or online multiplayer gaming, where waiting for a dropped frame just causes terrible, unplayable lag.
Now, what's really fascinating about TCP is how it actually sets up that reliable connection in the first place. This is the famous TCP three-way handshake, and I promise you, you will be tested on this exact sequence. Step 1, SYN. The client reaches out and asks to synchronize. Step 2, SYN ACK. The server acknowledges that request and agrees to it. Step 3, ACK. The client acknowledges the server's agreement. It's exactly like sending certified mail. Both parties confirm they are fully ready and listening before a single byte of actual data is transmitted.
Getting to the top now. Section 5, Layer 4, Application Layer, the user interface.
We've reached the very top of our stack. This is the layer closest to you, the human being. It acts as the ultimate bridge, translating your everyday clicks and keystrokes into the network data that cascades all the way down the layers we just explored. To understand a major protocol here, just ask yourself, do you memorize complex IP addresses like 142.250.190.46 just to browse your favorite websites? No way. You just type in google.com, and that perfectly illustrates the absolute necessity of DNS, the domain name system. DNS acts as the internet's automatic phone book right here at the application layer, instantly translating human-readable domain names into the numerical IP addresses the network actually needs to function.
Now, for your exams, memorizing application layer protocols and their corresponding port numbers is just a massive points earner. These are basically free points if you lock them in. HTTP, for regular web traffic, uses port 80, while the secure, encrypted version, HTTPS, uses port 443. DNS, our internet phone book, operates on port 53. If you're sending an email out, that's SMTP, running on port 25. Transferring files, that's FTP on port 21. These port numbers are exactly how the transport layer knows which application layer service to hand the data off to.
All right, Section 6, the real-world scenario, putting it all together.
We've studied all the theory, layer by layer, but networks don't operate in isolation. Let's synthesize this whole explainer by watching the data beautifully cascade down the entire stack the second you click to load a YouTube video. First, at the application layer, DNS finds YouTube's IP address and an HTTP request asks for the video. Second, moving down to the transport layer, the server decides to stream that video using incredibly fast UDP datagrams so you don't suffer through buffering. Third, at the internet layer, global routers use IP addresses to direct these packets across entire continents. And finally, at the network access layer, local switches use MAC addresses to frame the data and send it over your physical Wi-Fi router directly into your phone. And the crazy part? This entire process happens in milliseconds. So as we wrap things up today, I want to leave you with a slightly provocative thought. As you watch this very explainer, exactly how many UDP datagrams and physical frames is your specific device processing through layer 1 right at this exact second? Think about it. Every pixel of video you're seeing, every sound wave of my voice is currently moving through these exact 4 layers to get to you. Use this framework, study these layers, and you are absolutely going to crush your networking exams. Keep learning, keep questioning, and we'll see you in the next explainer.